Okay, thank you very much. Hi, everyone. So to make things very clear, I'm not at all a student of Paul Tapponnier. I've never worked with Paul Tapponnier, but as many of us here and around in France and in the world, I've been deeply influenced probably by his work. So that's why I wanted to be here today. So I'm a field geologist, basically, and with age coming, I evolved toward very large-scale stuff, trying to relate continental deformation with mantle convection. So ça marche pas. Okay, so let's start with the way we see the deformation of East Asia. So no need to comment this. We have seen this already this morning. And this is also very obvious in this room and at this occasion. So I'm not showing you these images that everybody knows for scientific purposes, but just to point out that this is only one of Paul Tapponnier's contributions, many contributions. But it's very important, especially to me, because at the time when I was a student and a young scientist, these images triggered a very intense debate at that time. Whether you liked it or not, you had to take side in this debate, in this period. You had to be in favor of extrusion or against extrusion. And among geologists, it was not always easy. Okay. And also, this is important because, of course, Paul Tapponnier, and this was said this morning, and Peter Molnar opened our eyes to very large-scale deformation of continents. And as I write here, as no one had since Émile Argan. Okay, so that's why, for me, Paul Tapponnier's contribution is really very important. A second point is that all along the 20th century, tectonics, the progress in tectonics, have walked side by side with the progress in geodynamics, and especially mantle geodynamics. It's quite obvious if you read Joly, Emperor, Holmes, Runcorn, Mackenzie, that plate tectonics is only the visible side of mantle convection. But still, if you compare these two models, on the left, Paul Tapponnier's model, on the right, one of our own models, I won't comment the differences. There are differences. The main difference is that on the left, extension in the South China Sea, for instance, is a direct consequence of strike slip faulting, while on the right side, extension is imposed by the rheology of the lithosphere that is floating on the asthenosphere here, and it's spreading by its own weight here. But this is not my point here. My point is that in none of these models, and many others at that time, had subduction any active role. Okay? So the eastern boundary was considered a free boundary, and even less mantle convection. Yet, if we look at this simple map of Africa and Eurasia, we see that, of course, we have compression and crustal thickening in front of the indenter. That's quite obvious. But the entire eastern part of Eurasia is supported by a thin lithosphere, and it's been affected by extension all through the Cenozoic at the same time as compression was thickening the crust underneath Tibet and the Himalayas. And we have complex interactions between these large-scale fractal faults that we all know of, so dextral and left lateral, and back arc extension due to the retreat of the Pacific subduction. And so extension in Eastern Asia is, that's for sure, largely due to subduction dynamics and not only to collision. So if you compare the surfaces, red surface and the blue surfaces, you see that you have on this old reconstruction of mine, you have more blues than red, and some of the extension here is probably not a direct consequence of collision, but it interacts with collision, and that's a very important point. If we now look at this map here, we see again, as Anne was showing this morning, this Tatian slab here in violet color shown by tomographic images at 1,000 kilometers, so in the lower mantle. You see that that may trace the shape of the former Asian margin in the east, and probably take it simply, the place where the former subduction might have been. You see that in the east, southeast here, the present-day trench has retreated toward the south compared to that position, and in the north, the trench has advanced, just like Anne said this morning. So if we now look at the geometry of slabs, so this is a drawing which I like to do of the geometry of slabs. So you have the Pacific slab on the right, Philippine Sea Plate slab, and the Indian slab in lithosphere in this sort of yellow-orange color here. We see a very different behavior with, on the eastern side, retreating slab, and on the side of India, if you do a cross-section across the Himalayas and Tibet, we see an advancing slab. So the difference is like this. On the top of this third image here, you have a retreating slab. So that's the case along the Pacific margin, and a back arc basin opening, specifically here the Sea of Japan. And the lower diagram shows you the advancing slab, where the suture zone and the Indian lithosphere has overridden its former portions that are now in the lower mantle. So a very different behavior on the southwestern side and the eastern side. Let's have a look now to the trajectories of absolute motion. So this is in a reference frame that is constrained by paleomagnetism. It's the reference frame designed by Trond Torsvik. And you see that it's over 50 million years. So you see that, and the background, sorry, the background is the tomographic anomalies in the lower mantle, just above the core mantle boundary, and you see this huge, very low velocity, shear velocity in the lower mantle beneath Africa and part of of India. And in blue, of course, you see the sort of slab graveyards in below the Eastern Asia. And you see that the continents, I'm talking about Eurasia and Africa, they are moving from the top of the low velocity anomalies, so the source of the main plumes, toward the graveyards where all the slabs finish their lives in the lower mantle. Okay? So that's the first order motion during the last 40, 50 million years at this very large scale. On the other side, of course, we have the opposite direction with the Pacific, the flow in the Pacific. If we now look at the mantle fabric, and this is here the seismic and anisotropy from the model, the S-wave model by Schaeffer and Lebedev, and we are at 200 kilometers. What you see is that the main flow direction, if we consider that this shearing is due to mantle flow, is as reported by the the reconstructions from the southwest to the northeast, and of course on the other side on the Pacific. So to make a long story short, the way we understand this is something like this. Here you have a cross section crossing the Indian Ocean, India, the Himalayan suture zone, Asia, the Sea of Japan, and the Japan Trench. You have on this side here the plume that is underneath Africa, and then this plume is moving toward the northeast here, and then we have the subduction zone here. And on this side, we have the Pacific lithosphere that is subducting underneath Japan. So this would be 45 million years ago. Okay? And the way we understand things is like this. We have the advancing slab here, okay, with the India overriding the subducted part of the Indian lithosphere, and on this side we have the Pacific slab, Pacific subduction retreating toward the east. And you see that the sense of displacement is the same as it is carried by the large-scale flow of the continent that I showed before. If we go upward, and if we look at the same sort of information, but 100 kilometers deep, we see a different picture. So we are in the lithosphere or near the base of the lithosphere here, and we have a very different geometry, especially in this region here, and where we see a flow here that is very similar to what is modeled with numerical means here by Sterna and others in 2016 here, okay, to the east of the collision zone. So if I try to synthesize what I just said, we have the India-Asia collision here that creates all the faults that are here in red, and of course, crustal thickening in Tibet. Okay, that has been demonstrated, especially by Tapponnier and his team. Okay, and these large-scale strike-slip faults here, they accommodate the transition between crustal thickening here and crustal extension here in East Asia. Whatever the exact correlation you assume between the faults and the background basin, but you have this transition from extension to compression and vice versa. Second, we have, this is the first big picture that we see at the surface. Then we have the large-scale conveyor belt that Anne was mentioning this morning, which is the big main flow from the plume underneath Africa all the way to the Pacific subduction here. And this is the large-scale convection. So we have here the slab, it is overriding, and here we have the retreating slab in the same eastward motion. And then we have at the scale of the lithosphere, we have a different flow, which is this toroidal flow here, east of the collision zone here, and the mainly in India, Australia slab here retreat that is opening the space for the extension in Southeast Asia. Okay. So that's the three factors, three engines that will shape the deformation of Asia in our view. So in the second part, I'd like to focus on a very different topic, that is the relations between continental rifting and mantle convection. So as you know, there are two different types, two main end members in rifting. We have passive rifting here, where rifting is mostly due to extensional forces at the boundary of the system here. Usually these passive rifts, they are associated with little volcanism, and they lead, if they go all the way to oceanization, to non-volcanic margins. On the other hand, we have active rifts here, where below the rift we have a mantle plume, here of various sizes. And most of the extension is driven by lateral gradient of gravitational potential energy here. Of course, you need to have some extensional boundary conditions to make it possible. And this question has been tackled for many years when looking at the West European rift system, whether it is an active or a passive rift. As you know, it's a rather short-lived rift, sometimes in the Eocene and Oligocene, all the way to the early Miocene. It is associated with magmatism, here, alkaline magmatism. It continues in the south here. There's lots of magmatism also in the Valencia basin here. And it intersects here with the back arc basin that we have here between Corsica, Sardinia, and Iberia and the main Europe, and it intersects also the Pyrenees here, okay? And it's partly coeval with the Pyrenees. So if we look at tectonic timing here, so forget about all this, I have no time to comment too much, but what's important to observe is that the formation of the Pyrenean topography here, that's the red lines, or the exhumation of the actual zone of the Pyrenees, so presumably also formation of topography, it falls just at the very end of a shortening period in the Pyrenees, and very close to the transition between shortening and the post-orogenic extension or evolution of the Pyrenees. And about at the time when the marginal basins, the back arc basins in the Gulf of Lion, for instance, started to open here. Okay, and we have a huge uplift at that time. So, what is it driven by the intrinsic evolution of the mountain belt, which is very strange if you consider the timing here, or is it a deeper process involving the mantle? So that's a question we have been addressing recently. And for this, we compare the West European rift system and the associated magmatism here. You see all the stars here from the Canaries, Cape Verde, and all the way to Western Europe here, with the magmatism in the East African rift system. So what we see is that this magmatism and the two rifts here, and also the Cameroon line here, are all associated with anomalies, positive anomalies of residual topography. Residual topography is the topography that cannot be explained by simple isostatic models. So implying that something is going on in the mantle underneath the lithosphere here. And these anomalies, of course, it's the most obvious is for the East African rift, and it goes all the way to the Red Sea toward the north here. It's quite clear also here underneath the Cameroon line, and it's quite obvious in Western Europe and all the way to Western Africa. If we now look at seismic tomography, this is the S-wave model of Schaeffer and Lebedev and more recent evolution of this model. You see that we have thin lithosphere here. We are at 200 kilometers, rather thin lithosphere here with an anomaly, a hot anomaly here, slow velocity anomaly that goes all the way to eastern Turkey here. We have this one that is very obvious too, and we have it here also underneath Western Europe. Here we have the same map as before with the non-residual topography anomaly, and all the dots here, the blue dots, they represent the absolute motion since during the last 40 million years of Africa and Eurasia, still in the same kinematic models of Trond-Torsvik. And you see that these anomalies here and these ones, they are parallel to the absolute motion. If we Yes. Okay. If we now look at this tomographic model by Barbara Romanowitz, the model of French and Romanowitz here, you see that the mantle is organized with low velocity anomalies here. And these low velocity anomalies, they have the shape of fingers that are pointing toward the northeast here, okay, at different depth. And a simple way to show this is along this section across Africa, Gulf of Aden, Zagros, and Eurasia. So we would have these deep anomalies, and then these deep anomalies, they go up in the lower mantle, they reach the upper mantle, and they form these fingers that are pointing toward the northeast. And this is parallel to the absolute motion of those plates. So we have actually different types of rift. We have the classical rift that I call B-type here. And this classical rift is mostly oriented perpendicular to the main flow in the mantle. Okay. That would be, that's how we imagined the mid-Atlantic rift, for instance, at the beginning. Okay. And we have another type of rift where the rift is oriented parallel to the mantle flow that I call A-type rift. Okay. And if you look at the different rifts we have in that area, the most typical A-type rift would be the East African rift here, and where I cannot detail here all the data that exists concerning seismic anisotropy, but the flow of mantle flow here really seems parallel to the rift. We have B-type rifts that are oriented perpendicular to the mantle flow here or here, Gulf of Aden. And what we propose is that in the Oligocene, the West European rift was an A-type rift, of the same kind as the B-type rift. And in our view, this sort of rift that can be very spectacular at the surface is usually very slow, less than a centimeter per year, most likely half a centimeter per year maximum. And if nothing changes in terms of kinematic boundary conditions and so on, this rift will never evolve as an ocean. Okay, this one would evolve as an ocean, but not this one. It's an assumption, of course, but it's how we see it. So how did things happen? So what we proposed that some 35 million years ago, we had this finger of African mantle reaching all the way to Northern Europe with an A-type rift forming on top of it. And then after that period, starting at 32 or something in that area, we had the opening of the back arc basin, the slab retreats. And this slab retreat was very active. If you consider the central Mediterranean here, the position of the trench that we see here, nowadays is 800 kilometers further to the southeast compared to its initial position. Okay, so you cannot have here 800 kilometers of retreat toward the southeast without a strong mantle flow in this direction that would affect a large part of the area. And this would have destroyed this finger that we have here. So I will not elaborate any more, but this is an attempt to classify the different rifts with an horizontal axis that would be this difference between A-type rift and B-type rift, and a vertical axis where we had active rifting here and passive rifting here. And so here we'd have the East African rift, the ECRIST, West European rift system, probably the Rio Grande rift also in western US. And here we'd have very typical rifts like the Menderes rift, the Corinth rift, maybe the North Atlantic rift, and other rifts would be oblique and intermediate here. And to finish up, I made this I didn't make this reconstruction. I used reconstructions made by Torzvik and Cox in their famous book. and I put in them the main rifts at the Permo-Triassic transition and in the early Jurassic here. And these are the A-type rift, and these are the B-type rift, if you consider the absolute motion of plates at that period, shown by the arrows here from these reference here. And you see, for instance, that at 250 million years, the Karoo 1 rift here, that did not evolve into an ocean, only much later, is parallel to the flow and associated to a lot of volcanism and probably to a plume. Same for in Western Europe at that period. The North Sea rifting did not evolve into an ocean before many million years later. Even the Siberian rift here died at an early stage, and only in the early Jurassic, after the early Jurassic, the Karoo 2 rift finally evolved into an ocean, but this took many million years. So while this main station rift here was, since the beginning, probably a B-type rift, and it evolved into an ocean. Well, thank you. That's I wanted to say.